Okay, lesson 7. Let's move on to a bit of contact analysis in nonlinear static. I think sometime back we discussed in one of the lessons, rather the nonlinear theory part lesson, wherein contact is actually a nonlinearity. That is, the stiffness is changing over a period of time, and obviously that makes it a kind of nonlinearity. So in this example, this is an interesting example. We have all the possible nonlinearities. We will be having large displacement. We will have material as rubber, which is also nonlinear, and finally contact is as well present. Okay. Secondly, we will also see how to overcome instabilities typically seen in a nonlinear analysis, wherein such kind of connections come into picture. So this one it is an example of a rubber tube which has been subjected to two loads, one in the horizontal and the other in the vertical direction, and we are going to see the behavior of this particular tube under those loads. It is being connected at these locations down here, somewhere here, and we will see how it works after the application of loads. So let me move into the software. Let me get into the software. If I check this setup, we actually have two configurations. Okay, the default configurations looks like this. Obviously, or it is obvious that this can be treated as a symmetry, and I can take half geometry down here, and let me get into the study. So first, I can create a nonlinear study as usual, nothing out of the way. Both the metal and the rubber are treated as solid materials, solid elements, so that's fine. In terms of restraints, let me take the easier ones first. So in terms of restraints, we have a immovable restraint at the bottom, wherein we are saying it is held firmly. We have a symmetry condition somewhere at the center down here, and the stabilizing thing let me discuss a little bit later. But before that, in terms of contact, we are giving no penetration contact at the host locations down there. Okay, you can see that one is this and the second one is down here. Okay, so we the other important thing that has been done in this is the rubber component. In this case, we are using Mooney-Rivlin constants, two constant model, and the constants have been directly given to the software. So this 1.2 and 0.007 is given by us. So in the past chapter or the last chapter, we saw that we can the software has the capability to convert a stress strain curve into Mooney-Rivlin constants. Typically, this is what is also called as curve fitting, wherein we derive the constants, and then we can derive a curve out of the equations that these constants represent, right? So other way around, there are other softwares or tools by which we can actually derive Mooney-Rivlin constants based on the curves that we have, or for some material people directly give Mooney-Rivlin constants. You can directly take them and give it to the software. So this is what has been done here, wherein we have the constants and we are giving it to the software directly. Let me check the setup in terms of properties. So I think there is no much difference here. Typically large displacement, the time step increments are the default ones. We are using force, we are using Newton-Raphson, and this is the way it proceeds. So this is the setup. Let me try to solve this with the discussed boundary conditions. Yeah, one more important thing which I would like to highlight. Mesh is very important, especially in the case of contacts. So ensure that all those appropriate faces are selected and we have a comparatively fine mesh at those localized locations. Okay, so this is what it is all about. Let's see how the mesh looks first. Okay, you can see definitely at contact conditions we have a finer mesh so that contacts do not fail and there is enough scope to converge. Of course, this rubber component can have a finer mesh, but it's okay for a fast analysis, and this is the way the setup looks. Let me try to solve this one. It gives surface to surface option, might give a better accuracy. So at the moment I don't want it. I say no and I proceed with it. We can expect a failure down here. So while this does, let me scroll through the setup. So we created this, we created a study, we gave the Mooney-Rivlin constants. What else? Yeah, these are there. Holding the geometry, symmetry boundary conditions, the load is applied, applying a vertical force, exploded view of the setup. To exploded views can be used to create these contacts. It makes it easier. Yeah, I missed out in terms of friction. We are giving a value of 0.1 for both the no penetration contacts. One of them is being treated as surface to surface contact, and the other one is treated as node to surface contact. And mesh controls, that's what I say. You can either give at the component level or select the appropriate surfaces and give it. We want to ensure a finer mesh around. Okay. Yes, we can trigger this analysis. Frankly, it is a bit time consuming one, but I am holding on to see a failure. I think the failure has already occurred. Let me check. No, not it. Okay, so while this goes on, let me also cover a few more things. So in this case, if I see the software, if I go back to the software, if you see, because of this top load of 550 Newton, which is on the top surface here, the gray part or the rubber part is going to go down. We expect more amount of movement over there. However, because this is not a dynamic analysis, time is not involved, it is actually a static analysis. So obviously there will be huge amount of deflections which are unrealistic, and the convergence would stop. So this can, if it happens on its own, then this can go at a high speed. The contact down here may not be detected, and it may penetrate and it will go off. However, we can stabilize this setup by applying this thing called a stabilization vertex, and we'll see how it is applied. Instead of making this video long, I would like to pause for a moment so that this solution goes on. And okay, before that, let me check if any other important thing is discussed in this text. So yes, this would be typically seen as stiffness singularity, pivot errors. These are the common errors that we will be able to see here. And to stabilize it, what we do is we hold a particular node down there, and we apply a displacement equal to 66.04, which is equal to the length of the gap over there, so that the deflections that are happening are slow and driven by the displacement boundary condition. That will help in stabilizing the model, and we can get a faster accurate result. So once you complete, you should be able to see this, wherein the model is going to come down. It would almost touch the bottom, and the further deflections are happening, and those are more realistic. Obviously, solution is going to converge, unlike what happened before. Of course, you can validate it by seeing the point where it is touching, and that tells us how it is going to touch, and whether the 66.04 displacement that we give is realistic or not. So this also tells the limitations of static analysis. Obviously, this setup in one way, because it is not considering the inertia, it needs a dynamic analysis, and a static analysis cannot include time effects or inertia effects. So that needs to be understood and taken care of. And yeah, pretty much that's it. So let's see the solution. Let's see how it. You can see that in the warnings window, it is already saying that the solver has numerical difficulties, non-converging gaps, automatic reset is required. So you can also observe that it has reset it until fifth step. So 5 times it has gone back, and the time step that it is using now is very small, of the tune of 0.4031, right? So obviously this has failed. I'll say okay. I'll see stop. Let me check if any results are there. No results. That's fine. So now I unsuppress this one, the boundary condition used to stabilize the model. So on the rubber component, we are selecting the vertex down here somewhere, right? This vertex is selected. A reference geometry is given, and a displacement in a linear way is applied so that it goes down. We know it is going to go down, so we can safely do that. As well, giving this boundary condition will make it go down with a certain speed, which is quite stable. So now, obviously, we should be able to see more convergence, better convergence. Let's see how it goes. Wish to see some results on the screen, but this is what it is all about. While this happens, let me check. Yeah, these questions you can go down through your own. So in one way, by the way, the exercises in this study are nice. You can explore it. It gives a very good application-oriented exercises, very useful. The gear thing is a very common application. We also have the rubber seal, another common application. And yeah, pretty much that's it. So only one lesson remains. It is on metal forming. We will cover it in the next recording. In the meanwhile, I think this solution is going on. Looks okay. So I think instead of making this video long, I'll pause it for a few seconds and come back once the results are there. Okay, let's explore the results. It took a bit of time to solve. As well, I would say you might face some convergence problems while you do this. So my suggestion, all the knowledge that you have gained from this nonlinear training will be useful in troubleshooting this setup. If you see the results here, and if I animate, obviously the 64 millimeter or 64 unit displacement that we give is helping to stabilize the setup. It is taking this part down, and that helps in solving the details. Otherwise, all other results are typically one mesh stress, displacements, etc. So this is what it is all about. I think I think this is what I would like to cover in this chapter. If you continue to face any convergence problems, please approach me. I'll try to help you out with the right settings. Okay. Thank you very much. Meet you in the next lesson and the last lesson for this training manual, which is on metal forming, lesson 8. Thank you.